I actually think we can do all of this work on this graph itself. So I'm going to place these two positive charges here. And can I get a volunteer to show me what direction these sketch a direction of electric fields from these charges using the arrows. So what direction would these electric fields go in? Which is very much related to what we did in class yesterday. Did you want to? It's going to go towards the negative, right? So electric fields are arrows, and I had a lot of students show that the path would be curved, but what you should notice is that the path would be curved if it was just one positive and just one negative. But it's a line of positives and a line of negatives. So it's going to be a straight path rather than curved paths from positive to negative, all the way across. And that's what happens when you create a line of positive and negative charges. It eliminates those curves and allows the electric field to create straight paths, and then we have a nice path for our proton to travel, right? The proton's going to go from positive to negative, and it's not going to have kind of that curved motion. This is how we create a straight line path for charges when we want to isolate the movement in a specific way. So from here, let's go on to question number 2. Which of these, A or B, is going to have the greatest electric potential energy? So remember, they're both protons for now. Or sorry, they're both positive charges, not protons. Protons can't move. But they have more positive protons than electrons, so they're both positive charges. Between A and B, which one is going to hold the most electric potential energy? Relate this back to our gravitational potential energy and our, what was the other one? Elastic potential energy. Any thoughts? Nathan? It's going to be A. So I want you to remember the fact that even though it's not energy, it's force, right? Force is proportional to 1 over distance squared. That's an important proportion that you want to memorize. Now, as the distance increases, this force is going to be really small, and as it decreases, as the distance gets smaller, this force is going to be really big. And if you hold those two charges together like a magnet, you are storing potential energy in these two charges, and by storing that potential energy, it has a capacity to create a large change. Or in this case, it would create a large kinetic energy. It would move much faster from here as opposed to here. Does that make sense? Introduction or connection between our energy unit and our electricity unit. Last question is, if I replace these with negatives, and we can ignore all this, my electric field, some scientists decided we're always going to have the electric field point away from positive and into negative. But what if I threw negatives in there? What if I threw in negative charges? How would my negative charges move? Can I get a new volunteer? Think about how charges in general interact with like charges versus opposite charges. What do you think is going to happen? Jack. It's going to move opposite. Even though the electric field lines are pointing to the right, that's the motion of positive charges. But it doesn't mean that we can't have negative charges in here, but the negative charges are going to move to the left. They're always going to move away from the negative and toward the positive. So when we get into electricity, we're going to focus on electrons moving because we know that electrons can move versus protons. And it's going to be very much related to your introduction of light bulbs and batteries, which is our activity today. So are there any questions on this warm-up?